In section 6.3, we're going to take those two-dimensional regions that we examined in section 6.2, and we are going to revolve them about either a horizontal or a vertical line and create a volume of revolution. So before we get into any definitions or any formulas or anything like that, I want to show you a really quick example. And I'm just going to use the function f of x equals just the straight line x and the x-axis, which as a function we would write as g of x equals 0. And I am going to find the region that's enclosed between these two functions from 0 to 3. And we're going to start off just looking at that region. So f of x equals x is just like the 45-degree line. Splits our first quadrant perfectly in half there with that diagonal line. G of x equals 0 is the x-axis. And then we just want to create the region that goes from 0 to 3. So we're going to drop a vertical line down at 3 to cut it off. So we've just got a triangle. So back in section 6.2, we talked about how we could find the area for that region. And what we're going to do here now in section 6.3 is we are going to take this region and we are going to revolve it around an axis. For this first example, we are going to revolve about the x-axis. And you're going to see here in this first section with slicing, that's typically what we're going to use slicing for, is revolutions about the x-axis. Now this is called also the axis of revolution. So we're going around the x-axis, and when we do that, sometimes it's hard to visualize on a flat piece of paper on the flat screen, but what's going to happen is this point up here is going to end up coming out towards us and doing a 360 all the way around that x-axis. When it gets to 180 degrees, we are going to have an exact replica of it. It's going to be the reflection over the x-axis. And we use the reflection to help us draw what the solid is going to look like. And then it's going to continue spinning back around the other side of the x-axis. And when it gets to 360 degrees, it'll be back up where it started. So to actually make this look like a solid, what we also do is we draw like these little arcs to try to make it look like it's coming out at us. Make that a little bit better. So that point came out at us and then hit the 180 and then went back in. And it did that all the way around. So what we've just created here is a cone, kind of sitting on its side. So we've got a cone. And we want to know what the volume of that is. Now, there is a geometric formula for volume of a cone, but we're going to be doing this with integration. So the whole idea behind volumes by slicing is we're going to look at just one little piece inside this region, and we're going to follow what it does as we do the rotation. So that's our representative slice. And when we take slices, we always do them perpendicular to our axis of revolution. So our axis of revolution here is the x-axis, which is horizontal. So the slice I'm taking is vertical. And we want to follow exactly what happens with that slice as it gets revolved. So I know I'm going to have eventually the reflection over the x-axis. And it's going to go all the way around, and it's going to be circular. And we're going to take just this little slice, and I'm going to draw what it looks like down here. I'm going to draw it a little bit bigger. So the way we have it drawn on the graph, it looks kind of like this. You can see that this face over here looks circular, which is going to be helpful. The basis for the formula of finding volume by slicing is definitely based on a circle. It might be more helpful if I actually look at it this way, though. Might be a little bit more recognizable if we lay it down. All this is technically is a cylinder. Our slices are just cylinders. And cylinders have volume. So right now, just in terms of geometry, the formula for volume of a cylinder is pi r squared h. Where the radius goes from the center out to the edge, and then the height is here along the edge. So if we know the radius of that cylinder and we know the height of the cylinder, we can find the volume for that one particular cylinder. Now, if we translate that back over here, the radius goes from the center out to the edge. So that's in the exact same spot as where we had it over there, and then the height is up here. And if we look at what this means in terms of the graphs on our function, that height really just looks like a tiny, tiny, tiny little x value. It's some tiny little distance along the x-axis. And then the radius goes from our axis of revolution up to the function. Now, because my slice is kind of thick, we see that this particular cylinder has a slanted height. But our goal is to make those cylinders so thin that you won't be able to see a slant in that height or any difference from the left side of the cylinder to the right side of the cylinder. So the way that we do that in calculus is, since it's a tiny little difference along our x-axis, we call that delta x. And then we said that height, or excuse me, the radius was the axis of revolution out to our function. So really the radius is just the function. So I'm going to go ahead and replace those. Volume is pi times our function squared, and then delta x, some tiny little x distance. We want to make it really, really, really small so that the variation in our function isn't going to make that much difference in the volume. Now, we'll get the volume of the whole entire solid if we split the entire solid up into lots and lots and lots of tiny disks and find all of their volumes individually and then add them all back together. And that's exactly what an integral does for us. An integral says along the interval from A to B, we're going to separate it out into lots and lots and lots of subintervals with length delta x. And delta x is the same as dx when we start translating this to calculus. And what we want to calculate along those tiny little subintervals is pi times f of x squared. This is just our most basic general formula for volume by slicing. Now, it's really important to note that this formula is only valid if the axis of revolution is being used as one of the boundaries, and in particular the bottom boundary. If it's not, we will see how we need to adjust this just a little bit to compensate for that. One other thing that's really important for the slicing method, which we also call the disc method, since we're making all these discs, is since we are going around the x-axis, when you use the slicing method, you always are going to set your integral up in terms of the variable that matches the axis of revolution. So your integral should be written in terms of the variable that matches the axis of revolution. Since we were going around the x-axis in this problem, everything in this integral is in terms of x. And there are three specific things we need to be careful about. The radius function is a function of x. I'm going to integrate with respect to x. And these a and b values are both x values. This is x equals a, x equals b. So all of those things are in terms of x since I'm going around the x-axis. And we're going to go ahead and calculate it for this particular problem. So our radius function here, we were going out to the f of x equals x graph, and we want the volume that's created from 0 to 3. So our volume is going to be 0 to 3 pi times our f of x was just equal to x dx. Now the pi is just a number. It's an irrational number. If you're going to integrate this in your calculator, or if you're going to use some sort of computer aid to help you with the definite integrals, you don't want to include the pi. Pi is technically just a coefficient. We want exact answers, and if you put the pi in there, it's going to multiply out a decimal approximation for pi, and that won't be an exact answer. So just leave the pi out of it for now. And we're just going to throw a pi on our answer. So we're really just going to integrate from 0 to 3 the x squared dx. And now it's x squared, remember, even though our function was x, it's x squared because our formula says square your radius function. And that all goes back to how we find volume of a cylinder. It's pi times the radius function squared. So that's why I have x squared in here. So now we just need to integrate. So the antiderivative for x squared is 1/3 x cubed. And we need to evaluate that at 3 and at 0, and then subtract. So at 3, 3 cubed is 27, but we want 1/3 of that. So we're going to get 9. And then at 0, we're going to get 0. So we just end up with 9 pi. That would be our exact answer. If we actually plugged the pi into the calculator and used that to help us with the integration, you would just get an approximate answer. And our calculator would actually say about 28.27. So be really careful when you're doing these problems. Check to see whether you're being asked to find an exact answer or an approximate answer. That's really important. Almost always we want an exact answer. So we're going to look at just a couple of more basic problems. Just like in the last section, we're always going to start with some two-dimensional region, and it's very important that we draw this region so we have an idea of what the top function is, what our limits of integration are going to be, and then the way that we set our volume integral up is really just dependent upon how that original two-dimensional region gets drawn. We are going to go ahead and reflect it over our axis of revolution and give it the little arcs so that we can see what it's going to look like as a solid of revolution. So let's look at another one. We're going to find the volume of the solid formed when the region bounded by y equals square root x, y equals 0, and x equals 4 is revolved about the x-axis. Now, they will always give you enough information to create a two-dimensional region. And then once you have your two-dimensional region, then we will revolve it to create the solid. So start with a picture of your two-dimensional region. So y equals square root x, that's our kind of like a half a sideways parabola. Y equals 0 is the x-axis. And then x equals 4 is a vertical line. So we see that we do have this region that gets enclosed here. In the last section, we could just find the area of that region, but that's not what we're being asked to do. We're being asked to take this region and revolve it around the x-axis. So when we start to spin this, when we get to 180 degrees, we are going to have an exact replica of it reflected over the x-axis. And then it's going to come up to 360 degrees back to where it started. So we always have this little circle there at the end to represent its path all the way around the x-axis. And that path is followed by every point on the graph. So we've got all these other little arcs as well. So when we look at just one slice, and drawing that little slice can be helpful because it can help you determine what your radius function is. In these first few problems, it's not that difficult, but we might see some more difficult problems later on where we do need to look at that slice to help us decide the radius function. We always go from we've got our axis of revolution, and that slice goes out to the square root graph. So the square root graph is our radius function. R equals square root. And then our interval, since we're going around the x-axis, we want our integral set up completely in terms of x. So our limits of integration are going to be x values. So we want to look on this graph and see how far to the left it goes on the x-axis, and that looks like it's at 0, and it is. And then how far to the right on the x-axis it goes, and that was given to us, that's 4. So for the volume, we're going to be integrating from 0 to 4. We always have a pi in this formula, and that's because we have these circular cross sections. Anytime you're dealing with something where you're using some sort of circle calculation, whether it's with volume or area or circumference, you're always going to have a pi. And then times the radius function squared dx. So our radius function is in terms of x. We're integrating with respect to x, and the 0 and 4 are values on the x-axis, how far left and how far right our original region, not expanded, but how far left and how far right it reached on our x-axis. So that's just the basic setup. We definitely need to clean this up a little bit before we're ready to integrate. The pi we can just forget about to the end because we want an exact answer. If you square a square root, they cancel each other out and just leave your integrand of x. Excuse me, your radicand. So we just need to integrate x and evaluate it from 0 to 4. So the antiderivative for x is 1/2 x squared. We need to plug in 4. 4 squared is 16. Half of that is going to be 8. And then plug in 0, we're going to get 0. So this volume that we just created has a volume of 8 pi. And we're going to look at one more real quick. This one's a little bit trickier. We're going to find the volume of the solid of revolution formed when f of x, when the region bounded by f of x equals x squared and g of x equals 9 in the first quadrant, is revolved about the y-axis. So that's one thing that's going to be a little bit different in this problem, where we're revolving around a different axis. So you might want to look back and see what we're going to do a little bit different in this problem since we're going around the y-axis. We always want to start with a picture of our two-dimensional region, but I'm going to scroll back up in the notes here so we can remind ourselves what exactly has to be done differently if we're going around the y-axis. So we said here the integral should be written in terms of the variable that matches the axis of revolution. So in this example, if we're going to go around the y-axis, that means I want everything in my integral to be written in terms of y. Now I'm not going to go ahead and make those changes now. I'm going to draw my region first. So for our region, it says only use the first quadrant. We don't care what's happening in quadrant 2, 3, or 4. So we've got our f of x equals x squared, which is just our basic parabola. And we have g of x equals 9, which is a horizontal line up at y equals 9. So here's our f of x equals x squared. Our g of x equals 9. And if they want us to stick in the first quadrant, that means they also want us to use the x-axis and the y-axis if we need it. We don't need the x-axis because that square root function is serving as our bottom boundary. The g of x equals 9 is serving as our top boundary, but we do need that y-axis to stop us from going into quadrant 2. So this is our region. That's our two-dimensional region. We want to revolve it around the y-axis. We're going to spin it this way now. So when we start to spin, we're going to get to 180 degrees and we're going to have the exact reflection of it here over in quadrant 2. Oops. And then as it proceeds around to 360 degrees, it's just going to end up where it started. And every point on our function is going to do the same thing. So it's going to look circular all the way around. So it kind of looks like a bowl, except this is a solid object. There's no hollowness inside. We've got it on the outside, it looks like a bowl, but if you were to try to look inside, there is no inside to it. It's perfectly solid. So for this one, because we're going around the y-axis, we need everything to be in terms of y when we set up our volume function. We also said that when we draw our slice, it's going to be perpendicular to the axis of revolution. So this time our y-axis, which is our vertical axis, is the axis of revolution. So when I draw my slice, I need to draw it horizontally. So this is my little representative slice. That slice helps you to identify the radius. So our radius goes from the axis of revolution out to the f of x equals x squared graph. But we need to rewrite this in terms of y. This is technically y equals x squared. Right now it's solved for the output variable of y and the input variable is x. We want to switch that around so that the output variable is x and the input variable is y. And we can do that if we just square root both sides. And what we get is x equals square root y. That's what we're actually going to use when we set up our integral. It's the same exact function. It creates the same exact graph. We just need the y representation for it to use in our volume formula. And then let's see what else we need. Let's start to set this up and see what we're missing. So I've got integral pi radius function squared, and I know I'm going to be integrating with respect to y. We need limits of integration, and since we're going around the y-axis, they have to be y values. So I want to know how low this graph goes on the y-axis, and I want to know how high it goes on the y-axis. So it goes all the way down to 0, and it goes all the way up to 9. So we're going to be integrating from 0 to 9. And now all we have to do is clean it up a little bit and work out the integral, and we'll have our volume. And notice this volume looks very, very similar to this one, except their orientation is a little bit different. This one's kind of laying on its side, and this one is standing up. And also this one's a little bit bigger because it goes from 0 to 9. The last one just went from 0 to 4. So let's clean it up a little bit. I want to pull that pi out because I don't want to worry about that one until the pi until the very end. And then just like the last one, if you square a square root, they'll cancel each other, just leaving your radicand, what was inside of your radical. And we just have to integrate y. The antiderivative for y is 1/2 y squared. And we evaluate at 9 and at 0 and subtract. So if you plug in 9 squared is 81. 81 divided by 2 doesn't come out to be a really nice number. It does come out to be a nice decimal. You could change it to a decimal if you want, but you'll very often see this just left as an improper fraction. If we plug in 0, we get 0. So the volume for this one is 81 pi over 2, which is 40.5 pi, which is quite a bit bigger than the last one. The last one was only 8 pi. But we went out 5 extra units. We more than doubled the height of that bowl. So this is just the most basic explanation for volume by slicing. There are some different things that can be thrown into these problems that would cause us to adjust our thinking just a little bit. For right now, all of our regions used their axis of revolution as a boundary, and that makes these problems a little bit simpler. In the next video, we will see what we have to do for if we have 2 functions as a top boundary and a bottom boundary, and that bottom boundary is not our axis of revolution. We just have to adjust a little bit. We also have the option to revolve around lines other than the X and Y axis. We can revolve around other vertical or horizontal lines as well. So we'll also see exactly how to do that. And again, it's just a tiny adjustment. The base, this basic formula is always going to stay the same. Volume by slicing is always based on cylinder, so we'll always have this pi r squared in our volume integral, but we might just have to add some things or make some little adjustments, but we'll always see like a pi r squared in there when we're doing volumes by slicing. And you might hear me say, I know you've already heard me say this, but volumes by slicing is also referred to in a lot of calculus classes and calculus textbooks as the disk method.